Hello kids, I'm your magic mentor Chavi Bansal. I know it's been a while since we connected over YouTube, right? I didn't post any video, but it's okay. So today I'm going to start with a new chapter called as equilibrium. And to be very precise, we are going to deal with the chemical equilibrium. You guys might have heard about the chapter, right? It sounds very difficult, but trust me, it's very easy and I'll make it much easier for you people. Just keep posting your doubts in the chat window. And if you have any queries, you can raise a request and I'll be posting a video regarding it. Okay. So before we start, have you heard about equilibrium? Like what is equilibrium in a general day-to-day life? So what is equilibrium? It is just balancing. So whatever forces are there, what are the factors that are going to be there for a work to happen, right? If it balances out, it is called as equilibrium. For example, you might have heard people in the Middle Ages talking about work-life balance or balance between your studies and how much time you should spend on gaming, how much time you should spend for other activities, right? So there should be a balance. So when things are balancing out each other, then it is called as equilibrium. Okay. So let me start by sharing my screen. Just give me a second, guys. Yeah, one second. I hope you guys are able to see my screen, right? So we were talking about equilibrium. Just a second. So we were talking about equilibrium, right? So what is equilibrium? Equilibrium is nothing, just a balance between different factors, right? Now we are going to talk about the equilibrium specific to the sciences, right? In sciences, the equilibrium can be of two types. One is static equilibrium and the other is dynamic equilibrium. Now, what is static equilibrium? What is dynamic? As the name suggests, static means static. It's not moving. Nothing is moving, right? So for example, if I'm pulling something, for example, me and my brother are having fight for a chocolate. So if I'm pulling that chocolate towards me and he is also pulling the chocolate towards himself and both of us are able to pull it at the equal forces, then the chocolate will not move. It will be at the same position. That is called as static equilibrium. So for example, this is a box and there's a force in a forward direction and there's a similar force in a backward direction. So net movement, if initially the box was at rest initially also, so the net movement will be zero, right? So this type of equilibrium is called as static equilibrium, where the objects on which the forces are applied are not moving and not leaving its place, right? This is called as static equilibrium. Okay. Now, what is dynamic equilibrium? Dynamic equilibrium means still the forces are balancing out each other, still the factors are balancing out each other, but still there is a dynamic process. So for example, I have a tumbler, right? And I start pouring some amount of water in it. It already had some water and for example, height h, okay? And I started adding some amount of water to it, okay? Now, I didn't know that there's a hole at the bottom of the tumbler. What starts happening, whatever amount of water I'm adding there, it is getting leaked out of that tumbler because of that hole, okay? So what is happening? The level of the water in the tumbler will remain same. Why? Because the amount of water I'm adding is the same as the amount of water leaving the tumbler, right? But why is it called as dynamic equilibrium? Because the water that is added is being added to the height of the tumbler and the water that was initially present is moving out, right? So the things are changing, but the resultant is same. So water is added, water is removed, but the resultant is same. Such equilibrium is called as dynamic equilibrium. Fine. So now in chemistry, we are going to talk about dynamic equilibrium. Okay. We are going to talk about dynamic equilibrium. Static equilibrium, maybe we can deal in physics, but right now in chemistry, we are going to talk about dynamic equilibrium. Okay. Now, before I started this video, I talked about chemical equilibrium. What do I mean by chemical equilibrium? Are there any other types of equilibrium present? So basically, in chemistry, we have two types of equilibrium, chemical and ionic. What is chemical equilibrium? The equilibrium that deals with all the chemical reactions, the equilibrium that deals with the chemical change. Chemical equilibrium is the equilibrium that deals with the chemical change. Okay. Whereas ionic equilibrium is mostly associated with the ions, there are dissociation, there are association and all that. So ionic equilibrium deals with the dissociation of ions. Okay. So majorly we are going to focus in the chemical equilibrium right now. After we finish the chemical equilibrium, we'll be moving towards the ionic equilibrium. Okay. So let's start with chemical equilibrium. So we know the chemical equilibrium deals with chemical reactions. Okay. Now, the reactions can be of two types, and equilibrium is not applicable to all the chemical reactions. Equilibrium is only applicable to reversible reactions. So, can I classify the chemical reactions into two types, reversible and irreversible reactions? Okay. Now, what is irreversible reactions? So for example, you have a paper and you start burning it, right? So what will happen? The ash, the black color ash will be collected, right? And you can see some gas is also being formed. So basically what is happening here? The organic matter in the presence of O2 is burned to give heat plus CO2 plus H2, right? Now, is it possible if you collect that heat, you collect that CO2 and water to generate that paper again? No, right? So such reactions, which can only takes place in one direction. There is only forward reaction. You cannot reverse the reaction. Such reactions are called as irreversible reactions. Okay. So what are irreversible reactions? Reactions that takes place only in one direction. Okay. And such reactions also lead to almost completion, right? So the reaction will complete. So the paper will completely burn, right? It will not stop in between. So the irreversible reactions are the reactions that goes to completion, or at least almost completion, right? Or at least almost completion. Right? So I gave you an example where you burn in a paper. Such reactions are called as combustion reactions. So all the combustion reactions are irreversible reactions. What are the other examples of irreversible reactions? Mm. So for example, if you're carrying out a chemical reaction in an open vessel, right? And the components, the reactants are gases, the products are gases. In such case, the gas will leave the vessel, right? And you cannot reverse those reactions. So any chemical reaction which has a gaseous product and it takes place in an open vessel, those reactions are called as irreversible reactions. So what are the other example? Reactions involving gaseous products taking place in open vessel. So always remember, equilibrium cannot be attained in an open vessel if there is any component of that reaction is gaseous. It has to have a closed vessel to have a reversible reaction to attain equilibrium. Okay. Next, precipitation reactions. What are precipitation reactions? So if you mix two salts and at the end, the resultant, one of them is solidified and gets precipitated, right? So once the precipitates are formed, that part of the components are not going to take part in the chemical reaction, right? So such reactions are also called as irreversible reactions. Other than that, if you mix a strong acid and a strong base, for example, if you mix NaOH plus HCl, it will form NaCl plus H2O. But it will, if you mix salt, NaCl in water, do you find NaOH and HCl? No, right? So such reactions are also called as irreversible reactions. Clear? Now, so what can I write about irreversible reaction as a summary? So reactions that takes place only in one direction, that takes place only in one direction, right? What else? Mostly occurs in open vessel, right? It's in open vessel. Such reactions leads to completion or almost completion, right? Almost completion. So these are the properties of irreversible reactions. Is it clear? So equilibrium cannot be attained in irreversible reactions, okay? Because there is no balance happening. All the forces are making a certain things to move in one direction only. There is nothing reverse of it is happening. That's why such reactions are called as irreversible reactions, and equilibrium cannot be attained in irreversible reactions. So equilibrium cannot be attained in irreversible reactions. Okay. Next, we are going to talk about reversible reactions. Very important. And this is the one on which the equilibrium comes into play. So we have to understand the reversible reactions in detail. So next is reversible reactions. So now from the definition of irreversible reactions, you might be clear what are reversible reactions. Nothing, the reactions that takes place in two directions, forward as well as backward. Okay, so reactions that proceed in both the directions under similar conditions. Okay, it's not like once you did the forward reaction and next day you are performing the reverse reaction. No, in the similar conditions at the same time, similar conditions and simultaneously are called as reversible reaction. So there is a forward reaction and there is a a backward reaction. So for example, A plus B is forming C plus D. So this arrow, the two side arrow, this shows reversible reaction. Why? Because the upper part of the arrow shows the forward reaction and the lower part of the arrow shows the backward reaction. Okay. So such reactions are called as reversible reactions, where initially the product might not be forming the reactants, but later on, as the reaction proceeds, the product starts forming the reactants also. So there is a forward reaction as well as there is a backward reaction. So remember, we took an example of this vessel, this tumbler. So adding of water from the top is a forward reaction. Okay, and removal of the water from the bottom is the backward reaction. So this is a kind of reversible. This is not a reaction, but this is kind of an example of a reversible process where you keep adding the water and keep removing the water, because of which it is taking place in both the directions, like moving ahead also and getting removed also. Fine. So such reactions are called as reversible reactions. Reversible reactions always takes place in a closed vessel. Okay, performed in a closed vessel. Why is it so? Because if there is any component which is gaseous, it should not escape. If it escapes, you cannot attain the backward reaction, right? So if it does not, it should not escape. For that, we need to have a closed vessel, right? For example, what is the example? PCl5 gaseous is forming PCl3 plus Cl2. Okay, so this is an example of the reversible reaction. So what can I tell? So in a reversible reaction, there is a forward reaction and then there is a backward reaction, right? Now, what does equilibrium mean here and when it is attained? When the rate of forward reaction becomes equal to the rate of backward reaction, at that time, that position is called as equilibrium. When rate of forward reaction becomes equal to the rate of backward reaction, it is called as equilibrium. What does this mean? It means reactants are forming products and products are also forming reactants. But the rate at which the reactants are forming products is same at which the products are forming reactants back. So there is no net change in the concentration of reactants and product, but the reaction is taking place in both the directions. It does not mean the reaction has stopped. It means the rate at which it is proceeding further is the same as it is coming in a backward direction. For example, if you see there is an escalator which is coming down and you try to go up on that, so the amount of work you done to go up is same as you by the escalator in a backward direction, right? So net position does not change generally until unless you are moving faster or the escalator is moving faster than your speed, right? So such situations are called as equilibrium situations. Clear? Any doubt? Okay. So, one second. So when the rate of forward reaction is same as the rate of backward reaction, such situations are called as equilibrium. Okay. Now tell me, do you think the reversible reactions will lead to the completion? No. So they never reach to the completion. They reach to the equilibrium and then the rate balances out each other. So a reversible reaction never goes to complete conversion. Means all the reactants will never get converted to the products. Okay. So it can reach to 90% also, it can reach to 80% also, but it will never reach to the 100% completion. Okay. But they always achieve a state of equilibrium. Okay. They always attain a state of equilibrium. Now, equilibrium can be attained in a chemical reaction or it can also be attained in a phase transition. Means need not to be the reaction to take place. Even the phase transition can also be in equilibrium. For example, there is some liquid which is getting converted to gas. So this is also a reversible process, right? So equilibrium can be attained in this case as well. Clear? Now let's go and understand in detail like what is reversible reaction, what is rate of reversible reaction. Matlab, we have been using this term, no, the rate of forward balances out the rate of backward and blah, blah, blah. So what does this rate means? Okay, so what is rate of reaction? Rate is basically the velocity of reaction. At what speed the reactants are getting converted to products. So that is called as rate of reaction. And the rate of reaction is generally, okay, according to the rate law, the rate of reaction is generally dependent on the concentration of the reactants. So, for example, I have this reaction. Just a second. Hmm. So, for example, there is a reaction AA gas is BB gas is forming CC gas plus D and D gas, right? Now this arrow is the forward reaction and this arrow is for the backward reaction. Now, if I have to consider the rate of the forward reaction, so can I write rate of forward reaction is directly proportional to what? It is directly proportional to the concentration of A raised to power its stoichiometric coefficient and concentration of B raised to power its stoichiometric coefficient, right? This is the rate of forward reaction. Same way, can I find out rate of backward reaction? Now, for the backward reaction, what are the reactants? C and D are the reactants, right? So it will be equal to C concentration raised to power its stoichiometric coefficient and D raised to power its stoichiometric coefficient, right? So this is the rate of forward reaction and this is the rate of backward reaction. Now tell me, at the initial stages, when the reaction has just started, what will happen? When the reaction has just started, we will have only the reactants, right? A and B should be present in the vessel, assuming that there is no C and D. So what will happen? Initially, the rate of forward reaction will increase, right? And the concentration of A and B will go down. With time, the rate of backward reaction will also increase and the forward reaction start decreasing, right? And the concentration of C and D start increasing, correct? But as we go ahead, so rate of backward reaction increases and the concentration of C and D will also start going down. What do I mean by this? For example, this is the graph between the time and rate of reaction, okay? So initially, the rate of forward reaction will only be there, right? And it will be maximum because maximum concentration of reactants are present. So this will be the rate of forward reaction, rate of forward reaction. Okay. Now, initially, the rate of backward reaction will be very low, will be zero actually, because we do not have any reactants, means the products of the forward reaction. So it will start from zero, but it will start going up. Okay, so this is the rate of backward reaction. Let me write it down. Rate of backward reaction. And the reaction will proceed till the rate of forward reaction and the backward reaction balances out. And this position is called as equilibrium, where rate of forward reaction balances out rate of backward reaction. Okay. So can I say rate of forward reaction initially is maximum and then it leads to the lower rate, right? And rate of backward reaction initially is zero and it increases with time. Clear? And when the equilibrium is attained, when the rate of forward reaction balances out the rate of backward reaction. Clear? Any doubt? So to understand it in more detail, what we do, we make an ICE table. What is ICE table? I means initial concentration. C means change during the process. And E is the concentration of the reactants and product at equilibrium. Okay. So this was the rate of reaction. What happens to the concentration of reactants and product during this process? Okay. Let's assume there is a reaction A forming 2B. Both are gaseous. Okay. And we are given the initial concentration at T equals to 0, means initial concentration of A is small a. Right? What will be the initial concentration of B? 0. Now, what will be the change? See, change. For example, let's assume there is an X change in the concentration of A. So what will be the change in the concentration of B? It will be 2X. Why 2X? Because for 1 mole of A, 2 moles of B are formed. So for X moles of A, 2X will be the moles of B formed here. Okay. And at equilibrium, so what is left at equilibrium? The concentration of A will be A minus X, whereas the concentration of B will be 2X, right? So this is called as ICE table, which helps us to understand the initial concentration, the change, and the concentration at equilibrium, okay? So now this AX, this will vary depending on the given concentration and depending on the reaction. Fine. So what can we draw from here about equilibrium? We can tell equilibrium is attained In reversible reactions, right? It is always attained in closed vessel, right? Um, Chemical, the equilibrium is dynamic in nature, right? Dynamic in nature, how did we understand? A is still forming B at equilibrium, but the rate at which A is forming B is same at the rate where B is forming A. So it nullifies it. So the concentration of A at equilibrium remains constant. It does not change. Okay, I'm not saying it will be equal to B. I'm saying whatever concentration is, it is same. It will stay same at equilibrium. Okay. So equilibrium is dynamic in nature, okay, and concentration of reactants and products are constant, and rate of forward reaction is equal to the rate of backward reaction. Clear? So we draw a graph for the rate of reaction. We already did. Let's see again. So this is time. This is the rate of reaction. Okay. So the forward reaction will be having the maximum at t equals to 0, right? So once at t equals to 0, the rate of forward reaction will be maximum, and with time it will go down, right? Same way at t equals to 0, rate of backward reaction will be 0, and with time it will grow, right? So rate of backward reaction, and that is rate of forward reaction. And here it is equilibrium. Fine. Now tell me one thing. This is the graph between the rate of reaction and time. Will it be same for the concentration of reactants and product? No, right? Let's see how it will be. So time, and this is the concentration of a chemical species. So at time t equals to 0, what should be the concentration of reactants and products? For example, we have this reaction. Let's follow this reaction. AA plus BB is forming CC, and all are gaseous in nature. Okay. Now, initially, what will be the concentration? Let's see. Let's say the concentration of A and B is initially, this is X and this is 2X. Okay. So it will be X for A and it will be 2X for B, right? And with time, the concentration of A and B will reduce. Why? Because A and B will be forming the product, and initially the rate of backward reaction will be 0, right? So initially the concentration of A and B will reduce, and after certain time, it will become constant. Fine. What about C? Initially the concentration of C will be equal to 0, right? And it will increase until unless the equilibrium is reached. So the concentration of C. This is the concentration of B, this is the concentration of A, this is the concentration of C. And when it becomes constant, that is called as equilibrium. What is it called as? Equilibrium. So equilibrium does not mean that the concentration of A and B will be equal to concentration of C. It means the concentration of A at equilibrium will be constant. It will not change with time. Same way, equilibrium concentration of B will also be constant. It will not change with time, and same goes with C. Okay, it can be equal to the reactants. It cannot be equal to the reactants. It depends. So this graph for the concentration is correct, and even this graph for concentration is correct. This is also correct. This is time. This is the concentration. Okay. This is also correct. This is also correct. Okay, and this is also correct. So it necessarily need not to be same, but it should become constant. So all these graph, all the concentration of reactants and product with time is correct in case of equilibrium. Is it clear? Do you have any doubt? Okay, let's do one question. Okay, let's see if we are able to draw the ICE table, if we are able to, find out the value. But before that, let's understand what will happen to the net rate of reaction. Okay, what will happen to the net rate of reaction? Okay, so what is overall rate of reaction? So can I write rate overall is equal to the rate forward minus rate backward, right? This is the overall reaction. Now, if at time equals to 0, RB will be equal to 0, right? The backward reaction will be 0 and RF will be maximum. So R overall will be equal to RF max minus 0. So rate overall will be maximum at time equals to 0, right? Now with time, rate of forward reaction will decrease and rate of backward reaction will increase. So rate overall will decrease with time. Why? Because rate of forward reaction will decrease with time and rate of backward reaction will increase with time. Correct? So rate overall will decrease. And what is the minimum rate overall? Rate overall will be equal to 0 when at equilibrium. Why? Because at equilibrium, rate of forward reaction is equal to rate of backward reaction. Clear? So if I have to draw a graph of time and rate of overall reaction, how it will be? Maximum when at t equals to 0 and then it reaches to 0 at t equals to equilibrium. So this is t equals to 0. This is the time when equilibrium is attained. Okay. So this is called as overall rate of overall reaction. Is this clear? Okay. So next we are going to talk about law of chemical reaction. Now, what is law of chemical reaction? So we are going to talk about law of chemical equilibrium or law of mass action. Now, what does this say? Okay, so let us assume a reaction AA gaseous plus BB gaseous forming CC gaseous plus DD gaseous. Okay, now what will be the rate of forward reaction? Rate of forward reaction will be directly proportional to concentration of A raised to power A and B raised to power B, right? Now we know when we remove the proportionality sign, we need to put a constant. So let's write K forward, AA and BB, right? Now rate of backward reaction can also written in the same way, KB, C raised to power C and D raised to power D, right? Where what is it? Within the brackets, we are talking about the concentration and concentration is generally written in moles per liter. Fine. Now, at equilibrium, RF is equal to RB, right? So KF AA BB is equal to K backwards CC into DT, right? So let's do one thing. Let's bring KB here and let's take this here, okay? So what it will be KF upon KB equals to C raised to power C, D raised to power D upon A raised to power A and B raised to power B. This KF upon KB is called as K equilibrium or equilibrium constant. So I can write K equilibrium is equal to kf upon kb, or c raised to power c, d raised to power d, upon a raised to power a and b raised to power b. Okay, so we can write this K equilibrium as Kc also in terms of concentration when we are dealing with the concentration of C, D, A, and B. Okay, so now as we have already done the graph, the rate of the reaction graph, right? So, okay, instead of that, so this is how you find it out. So if you have a reaction, you can write the rate constant of or rate law or law of mass action for the given reaction. So let's do it for, let's take an example. So for example, you have a gas SO2 that is getting converted to, sorry, SO3 getting converted to 2SO2 plus O2. This is gas, this is gas. Okay. Let us assume the initial concentration, ICE table, right? So initial concentration of it, this is 1. Okay. And it is 0, 0. Now the change is 0.2. So it will be 0.2 plus 0.1, right? So what will be the equilibrium concentration? 1 minus 0.2, 0.2 and 0.1. Fine. Now, if I have to write the law of mass action, so can I write Kc equals to concentration of SO2 raised to power 2, concentration of O2 raised to power 1 divided by concentration of SO3 raised to power 2, right? And these concentration are the concentrations at equilibrium. So can I substitute the concentration of SO2 as 0.2 raised to power 2, as of O2 0.1 raised to power 2, and of SO3 1 minus 0.2 raised to power 2. So can I write this as 0.2 into 0.2 into 0.1 divided by 0.8 into 0.8, right? 1 by 4, 1 by 4. So 0.1 divided by 16, which is nearly equal to, once again, 0.8. So which is nearly equal to 100 by 16 into 10 raised to power minus 3. So 425, which is equal to 24 for 6 point into 6.25 into 10 raised to power minus 3. This is the value of Kc here. Okay. What is Kc? Why we are using Kc? Because we are using the equilibrium constant dealing in terms of concentration. Is it clear? So this is how we are going to use the law of mass action or to find out the K equilibrium or equilibrium constant. Now, what is the physical significance of this equilibrium constant? Why do we need to find out the equilibrium constant? See, if you can see the equilibrium constant is generally the product raised to power their coefficients, right? Divided by reactant raised to power their coefficients, correct? So if K equilibrium is very high, right, it means the concentration of products is high than the concentration of reactants, right? It means the reaction has been almost converted to products. Okay. So if K equilibrium value is greater than 10 raised to power 3, it means most of the reactants are converted to product. Okay. Now K equilibrium is if its value is nearly equal to 1, then certain specific amount, like appreciable amount of reactants has been converted to the product. Whereas K equilibrium is lesser than 10 raised to power minus 3. It means the concentration of products is very less. It means very less concentration of reactant has been converted to product. Okay, so this is the significance of K equilibrium, and it helps us to understand the rate of reaction and the extent of reaction that has taken place. Clear? Now, let's do a question based on this K equilibrium. Let me just find out a question 1 second. Mm, okay. Huh. So now there's a reaction. So what is the reaction? N2O4 gaseous getting converted to 2NO2. Okay. The equilibrium mixture had 4 moles of N2O4 and 2 moles of NO3, NO2. Okay. In 10 liter of vessel. Now, what do we need to calculate? We need to calculate Kc values. Now, in this question, we do not need the ICE table. Why? Because we are not talking about the initial concentration. We are not talking about the change concentration. We are directly talking about what are the equilibrium concentration, and we are given with it. Okay. So let me write down the Kc in terms of the product and reactant. So concentration of NO2 raised to power 2 divided by the concentration of N2O4. This will be the Kc value. Now we have talked about the concentration. And what is the concentration? Concentration is equal to the moles divided by volume. So what would be the concentration of NO2? It will be 2 divided by 10. Why? Because at equilibrium we have 2 moles of NO2 and 10 liter is the volume of the vessel. Right? Same way, what will be the concentration of N2O4? It will be 4 divided by 10. Right? So can I use these concentration to find out the value of Kc? Let's see. So 0.2 raised to power 2 divided by 0.4. So 0.2 into 0.2 divided by 0.4, 1, 2. So 0.1 is the value of Kc. Okay. So this is the value of Kc. That is that we have found out. Okay. So this is what is about chemical equilibrium. Basically, the introduction to chemical equilibrium. We have just covered the introductory part. We have just touched the introductory part of the chemical equilibrium. I hope all the things that we have discussed so far are clear to you. Like we have laid the foundation. Now in the next video, we are going to talk about a bit more complex stuff. We are going to talk about the Kp values. We are going to talk about the relationship between Kc and Kp. We are also going to talk about further many things, and we are going to do a lot of numericals. Okay. So I hope this question was clear to you and you do not have any doubt in this. In case you have any doubt, please post that in the chat. Okay. And I'll try to solve that there. And if it is not solved in the written form, I can make a video of the doubts there. Clear? Thank you so much, guys. Have a nice day. Thank you.